Alright, here's our final project for EGR 555, Mechatronics Device Innovation. Here we have our prototype design for the ShadeShift sunglasses. The way that these sunglasses work is that they have an electrochromic lens inside the eyewear itself, and it allows for the ability to change the tint of the lenses using a microcontroller and a small amount of electricity. So our design was based on trying to incorporate all of the current solutions that Dignity Health is currently dealing with for trying to give therapy to patients who have received traumatic brain injuries or are suffering from stroke or are recovering from any sort of like brain surgery. The goal of these glasses is to combine the existing elements of other devices that are already available in the market. So we decided to have 4 of the main things that are available on the devices and practices that are currently being used by Dignity Health. Our first one would be the electrochromic lenses that are able to be controlled using a microcontroller. These lenses are able to be controlled using the microcontroller to change the tint levels. So if someone is experiencing eye strain while indoors and the lights may be too bright, or just the area around them is bright and is causing them pain cognitively, then we can have these glasses change the tint level, and they can have sunglasses indoors that are controlled electronically. Instead of having multiple pairs of sunglasses, you can have just the one pair of glasses that help you see both indoors and outdoors. The next thing we tried to add was a way to customize or have adjustable hues that the patient can wear and see in different wavelengths. So here in the middle, you can see that we have different types of frames that offer different colors for the patient to wear. And instead of having several sunglasses of different types like there is currently available, or there are expensive versions that are electronically controlled, here we have a non-expensive accessory-like approach. In the back, you can see that we have another frame, and that one is actually for what we call stroboscopic visual training, where what's currently on the market is our lenses called Synaptec, and they have training goggles that help with cognitive repair and therapy. So the way that it works is that the film is actually opaque, and once you apply electricity via a microcontroller, you're able to actually change the transparency levels, so it can go from completely opaque to completely transparent within milliseconds. And finally, the last technique that we wanted to approach is called binasal occlusion. So over on the right, you see 2 tiny pieces that we used for the glasses that causes binasal occlusion. So the theory behind binasal occlusion is that by limiting the basically sensory data that you receive through your eyes into your brain, as you limit it, you can actually feel the relief on the brain from trying to process the images that you're seeing in real time. So by having these binasal occlusion attachments, we're able to have a way for the patient to have their binasal occlusion viewing at any time that they want, because currently the current method is to use tape to make the occlusion on the lenses, and if the patient doesn't want it and removes the tape, they have to go back into the office to have it reapplied. And so this eliminates that factor by making it so that the patient can have it on and off whenever they want. If they're having headaches and they don't want to use it anymore, they can easily remove it, and when they are told that they need to be using it, they can easily attach it back on. Now, I've been talking a lot about microcontrollers, and for our microcontroller choice, we're actually using an ESP32 dev board. So this ESP32 is actually an 8-bit microcontroller, and is able to actually send out different analog and digital outputs. we'll mostly be using digital outputs. That way we can have a controlled voltage output. We'll be using what's called pulse width modulation, or PWM for short. And the way that the PWM works is that once you change the duty cycle, you can actually change the amount of voltage that's going to different devices. So as we will see with the electrochromic lenses, as we change the duty cycle, it'll actually increase the amount of voltage that's going through the lenses, and you'll see that the lenses actually get darker. And with all the explanations out of the way, I can go ahead and give a live demo. So here we can plug in the ESP32 to our power bank. This is a normal 5-volt power bank. So as we plug this in, you can see that the microcontroller lights up, and that tells us that it is being powered on. Now, while the microcontroller is plugged in, we can plug in this cable. This is attached to the microcontroller. As you can see, this is just one continuously long cable that is about 5 feet long, or 1 meter, and we're able to connect this to the back of the lenses, and we'll be able to change the tint of the lenses. So while the glasses are sitting here, we can go ahead and press the buttons that are on the breadboard to the right, and as I press the buttons, you shall see that the lenses will be getting darker. So right now we are at level 0, which is no tint. As I press the first button press, it actually goes to level 1, level 2, level 3, and finally level 4. Now we can go the other way. We can go back down to 3, back down to 2, back down to 1, finally back to 0. And when you press the down button, nothing will ever happen when it's already at its minimum. And as you go back up to the full 100% darkness of it, it'll never go higher, so it limits the risk of the lenses being damaged. Now that we're able to control the lenses, I'll go ahead and put it back down to level 0, and we can then demonstrate how the different colors can actually affect the viewing angle. So as we see here, we have a blue tint. Blue usually is for energy and to have the person feel more energized or full of energy to be more active. So as you can see here, we do have several magnets that are in specific places. And on here, we do have magnets embedded inside the 3D print for the molds. So here we also have indicators that let you know which side is the back, which is the front. And so as soon as we put it onto the lenses, it just snaps in place. And we can do that with each of them. So with the blue, we can put this one to the side. We can use the green, and it just snaps into place. I'll go ahead and remove these. And we can use the last one. What's also cool about these is that because of the position of the magnets, you can also stack the different colors. So we can have a sort of purplish tint if we have both pink and blue. If we get rid of blue and put green on, we'll have a different color combination, more green heavy. And if we go ahead and make green and blue, we can put these on, and it makes more of a turquoise kind of color. And so with these different color combinations, you can actually have different wavelengths of light being perceived within your eyes. The best part about the way that the magnets are configured is that you can actually have them all stacked in place, and this makes it more convenient for the patient or the user or consumer, that they can carry these wherever they want inside of a case that it can come in, and they can have these at any time at their disposal. It's very light and also very thin, so the travel factor is basically non-existent. And now we can go into the next one, where you can see we have more magnets as in a very specific layout. Here we have the binasal occlusion attachments. So right here we have them stacked together because of the magnets, but as you pull them apart, they're actually two separate pieces. So when you attach them to the glasses, it'll actually snap into place, and it'll have the binasal occlusion. So all the binasal occlusion does is it limits the amount of imaging that your brain is processing, and these can also be removed at any time. And no matter what, if you put them on, let's say you put them on at a weird angle, let me go ahead and do that. If you put it like at a weird angle, you'll know it's wrong, but you'll be able to fix it easily, and it'll be the same no matter what. The way that the therapist will be able to make sure that each patient has the correct level of occlusion, because everybody's eyes are at different distances and are different. The patient or the therapist will actually cut these plastic fins out to the exact degree and angle that the patient needs, and so it'll eliminate the need for the patient to constantly go back to the clinic to reapply the tape. Another good part of this is that you can actually put the Hue lenses on top of the binasal occlusion, sort of like a sandwich, and it'll still have the same effect of the binasal occlusion, and it'll have the added effect of the tint level adjustment. And now, as I take these off, we can put these together, and they make a very thin and small piece that the users can also carry with them, the same as they can take the different hue frames. And so now finally we can show how the PNLC works. And so I'll go ahead and plug in the film. Now, as I plug in the film, you can see that it turns on immediately and it actually becomes clear. So you can see everything behind it. But as soon as I press this button, it'll actually go in a mode where it flashes intermittently between opaque and transparent. So the need for this is to have the stroboscopic visual training, and we can add this onto the front of our lenses, and it's the same magnets as the tint adjustments. It wouldn't be recommended to have the tint or the binasal occlusion to be added on to this for the stroboscopic training. This would be its own regimen, and the therapist can actually determine which times that these patient will be using this, and it'll only be for very specific training sessions. With this little controller, it's actually able to do different modes. So here we have the flashing, and as I press the button again, it actually has more of a fading effect where it'll slowly go in between and out of the opaque and transparent views. When I press it again one more time, it'll actually turn off and stay off completely, so it'll always be completely opaque. And as soon as I press the button, it'll immediately change back to being clear. I can go ahead and show the camera how it looks through the PNLC. So as you can see here, you can see perfectly fine through the film. And as I press the button to turn it into the flashing mode, it makes it so that it's completely opaque and you cannot make out anything behind the film. And once I press the button again, it'll go into the fading mode, where it'll slowly go in and out between the two different states. And of course, when I press the button again, it'll go into just the solid opaque mode. And of course, you can see the LEDs here, but if I wave my hand in front of it, I can block the light. But when I press the button again once more, it instantly changes to being clear. And so that's how it would look for the patient to be wearing these glasses. Thank you for watching this presentation. I hope you enjoyed, and I hope you were better able to understand our goal for this project. It was very enjoyable to work on this project, creating the different ideas for how we can combine these different technologies and practices, and how we can incorporate it into a feasible and compact design. So thank you for watching, and have a great day.